Okay, off we go. Welcome back, everyone. I hope everyone had a good break. Hope everyone's rested and recharged and ready for the sprint that is the end of the semester. And good luck with all of that. Don't forget the attendance quiz, attendance code, right here. It's easy to fall out of the habit during a relaxing break, but make sure to get this done. Clock's ticking. Okay, so picking up where we left off last time, we were talking about surface independence, and it's really a ripoff of an idea. So we have this old idea of path independence, and we went through and did the color coding last time and talked about how the same ideas, just kind of one dimension up, give this concept of surface independence. Now, just because I write down some ideas and say, here's what I would like such a vector field to do, doesn't mean that any vector fields can actually do it, right? But it's just pointing out that this concept, whether it's achievable or not, right? This concept is very analogous to this concept. Okay. Now, I like to see this kind of thing on the diagram as well. As y'all know, I'm a big fan of the diagram. This comes from a very legitimately natural place that's not something we can talk about in this course, but really the mathematically best, most powerful, most sophisticated way to treat all of this material is with this stuff called differential forms and chain complexes and co-chain complexes and blah, 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 and it's all powerful and awesome and not appropriate for this course. But when you boil off all the formalities and leave only sort of rubber meets the road, how does this apply to Math219? This is what you get, pretty much. So anyway, I strongly suggest that you organize all of your understanding, all of the ideas that you think about concerning vector calculus. Organize those ideas as laid out in this diagram. That's certainly how I do it. I think it's so helpful, right? And with this in mind, let me remind you, here's how we think about the special vector fields that we've talked about as early as chapter 6. We talked about these vector fields that are the gradient of something, aka vector fields where the curl is 0, aka vector fields that are path independent, namely if you give any two curves with the same boundary points, they'll always give you the same value for the line integral. So we know from way back when that every gradient is path independent. And I've claimed likewise vice versa, regularity issues aside, don't want to worry about that. Furthermore, I've claimed that curl being 0 is the local test. When the curl is 0, that's how you know a vector field is path independent and likewise is a gradient. How do we know these things? Well, check back through the notes. We used this theorem to prove that connection, and we used this theorem to prove that connection. Okay, so here's the speculation. This is wild, baseless speculation. But wouldn't it be nice if everything would just shift over, right? And then this idea here of surface independence that we just talked about, again, one dimension up, right? All the same ideas, but just one dimension higher. Wouldn't it be nice if every curl was surface independent? And wouldn't it be nice if this theorem allowed for us to prove that? And wouldn't it be nice if divergence being 0 was the local test? And wouldn't it be nice if this theorem allowed us to prove that? Now again, this is all wild and baseless speculation. I mean, the only reason I have to believe that any of what I just said would work is hope. Right? But it all works. And so this is about where we left off last time. And I'm just going to kind of point here. Let's see here. Yeah, we can do it like that. Why don't I go full screen? There we go. So this argument right here shows that if you have a curl, if you have a vector field that is a curl, claim it's surface independent. And how do I know it's surface independent? Well, when you compute it on one surface, the fact that you're looking at a flux of curl means you can invoke Stokes' theorem, just like the diagram suggests it might be useful. And Stokes' theorem says that gives you the boundary line integral. And then likewise on the other one, Stokes' theorem again tells you you can compute that with the boundary line integral. These two surfaces have the same boundary, means you get the same line integral, means these two fluxes are equal, means the vector field is surface independent. Now, a fun little game to play and to sort of, for your own curiosity, take this argument that we just made here, compare it with the argument that we made using the fundamental theorem of line integrals concerning gradients, being path independent. And you'll notice it's a rip-off. It is a bit-for-bit rip-off of that argument that we made back in Chapter 6. Just like the diagram suggested, right? So, in the same way that the fundamental theorem allows us to relate those, likewise, Stokes' theorem just allowed us to relate these. It's really, really a powerful analogy there. And then likewise, let's look at the business about divergence being zero. And I'm sure y'all recognize this little box that I've got down here. Right? We've looked at this kind of thing several times. And as we've already established, curls are surface independent. And if you're willing to believe these two statements are the same, because, how else? Look, if you've got some function where every integral is always zero, no matter what domain you pick, really, all the integrals are zero, no matter any domain, every domain, really, how could this possibly be? That integrand has to be zero. So if you believe that, then notice the thing that connects these is indeed Gauss's divergence theorem. So the thing that allows us to show that divergence equaling zero proves surface independence, Gauss's theorem is the trick. Again, exactly as predicted. Gauss's divergence theorem is what allows us to see that divergence equals zero is that local test. So, my gosh, the diagram was useful there, right? The diagram not only told us what we should suspect would be true, right? The diagram told us to suspect that surface independence might relate to these two statements. It also suggested how we might prove those two statements, and it was right about everything. So, again, my goal here is twofold, right? On the one hand, I wanted you to see how these arguments work, etc. But I also wanted to try to further persuade you that this is the way to organize these ideas in your mind. The analogies are so powerful, right? And you therefore don't have to remember various different equivalent facts about surface independence, like, as completely new pieces of information that you have to understand. If you think about everything in terms of the diagram, you could just say, oh, yeah, it's just like path independence. It's just slide it over one notch, same game. It's all the same. It cuts your workload kind of in half. Everybody see what I mean there? This is a big win, and it kind of blows my mind that more multivariable calculus books don't focus on how useful this little idea is. Okay. All right, so we have ourselves a new tool. The new tool is that divergence being zero is a test for surface independence. Surface independence is a way of saying that if you need to compute one integral, flux integral, as long as you preserve the boundary curve, you can instead compute a different flux integral, and you'll always get the same thing. So this is our new computational tool. Check that the divergence is 0. If so, you have surface independence. Pick any new surface you want. Just make sure to preserve that boundary. Okay, here we go. Alrighty. So let's see here. Here's the statement of the question. I want to compute a flux. Surface given, vector field given. And now notice, by the way, in the statement of the question here, it doesn't say use surface independence, right? Usually these kinds of questions will not announce themselves. They will not label themselves as this is a surface independence problem or this is a divergence theorem problem or something like that. Right? So you have to kind of look at the question, you have to understand exactly what's going on, and then pick the appropriate tool based on which tools are actually available. So, all right, let's do this. Our surface, it says right here, is this, what I've got drawn here in the drawing. It's the upside down paraboloid. Y'all remember from chapter 2, this is an upside down elliptical paraboloid. Z greater than or equal to 0 means I'm going to pick just the part above the XY plane. I've got that surface there. Let's see, it says oriented downward. Right? So that's why I pick the, what a lot of people might call inward. It's reasonable to call it inward, I suppose. I think even better than that would be to call it oriented toward the toward the z-axis. I think would make sense. Let's see how we're going to compute this flux. Well, let's use our shiny new tool. We're going to compute the divergence, which works out really nicely. The divergence is 0. We remind ourselves then, when the divergence is 0, your vector field is surface independent. Surface independence means, again, throw away your old surface. You don't need it anymore. Just pick any new surface you like as long as it's got the same boundary, and feel free to use that new surface. And of course, obviously, hopefully this is obvious, when we pick our new surface, we're going to pick with laziness in mind, right? We're going to self-serving the easiest new surface that we can think of, because why would we do anything else? Okay, let's take a careful look at our surface. Our surface is this. The boundary of that surface is that curve right there. Now let's take a moment to think about the, oh gosh. Oh no, I hit the side of my pinky finger hit the little scroll bar there, so now I'm way back. Okay, I gotta find where we are. Okay, there we go. Okay. Okay, so here's our surface. There's the boundary. There is a landmine that y'all have to worry about. It's real easy to mess this up. S says it's part of this paraboloid. This business about z greater than or equal to 0, that is a clarification. That's telling you which part of the paraboloid. It remains, this surface is part of the paraboloid. Right? What a lot of students, give me 2 seconds. What a lot of students think very often is, well, yeah, but what about that? Isn't that, I see that in the picture, isn't this included also? And very importantly, it's not included. That, what I have in blue, is not part of the paraboloid. Everybody see that? Now, it's easy to conflate this because the way we drew the picture, I kind of had to draw this purple ellipse in here because that's the boundary. That's how I know where my green surface stops. But when I draw that purple paraboloid, it looks like I'm drawing this blue I think I just said that wrong. When I draw this purple ellipse, it looks like I'm drawing this blue solid ellipse, but I'm not. Does that make sense to everybody? Yeah, so you had a question.
Yeah, so is there the only way for checking for surface independence, checking if the divergence equals 0, or is there another way?
Absolutely. If you want to know if your vector field is surface independent, we actually have 3 equivalent conditions, right? So divergence is 0 is kind of the computationally most convenient, but there will be situations that come up sometimes where the vector field is given as being a curl of something, right? And by the way, this comes up in physics. Curl, right, is a real thing, right? So the current flow field is the curl of the magnetic field. Right, so sometimes you literally know in advance that your vector field is a curl, and if that's the case, you don't even have to compute divergence. Every curl we immediately know is surface independent. Is that cool?
And how would we go about choosing if a surface is closed or open, and how does that relate to it?
Well, so that's I'm gonna talk about that in a bit. So can I defer your question to then? Yeah. Remind me if I don't get back to that, but I'm pretty sure we will. Yeah. Yeah. So for the moment, I want to keep our focus on this specific surface. Yeah.
I still don't get why the blue part is surface.
Yeah. Okay. So let me be a little bit more sort of explicit. So here's this, right, and that is this entire paraboloid that extends, infinitely downward. Okay, now here we have the clarification. This says, I want just the part of that where z is positive, or non-negative. So that says I'm going to look at the xy plane, I'm going to look at everything above the xy plane, on or above the xy plane. That's the part of the paraboloid that I want. Okay, well, yeah, but this what we have in purple again is just telling me which part of the paraboloid. What I have in gray down here is already off the table. It's not. It wasn't even part of the paraboloid in the first place. Does that make sense?
Yeah.
So here's another related point of confusion that's easy to, it's just easy to mess this up. You got to make sure to distinguish between a surface and the solid that maybe is enclosed in that surface. Or you might say a surface versus the solid whose boundary is that surface. Now the problem is we draw them the same, right? It's like the difference between a circle and a disk. Oh, let's see, I need a little bit of space. Here we go. So that's a circle, right? But if I draw that, you might think that I'm referring to the area that is that disk. They're not the same thing, right? The blue is a two-dimensional region. The red is a one-dimensional curve. Everybody see the difference there? Right. So we literally have different words for these. What's in red, that's called a circle. What's in blue, that's called a disk. They're totally different things. And in this situation up here, we've got to distinguish between the green surface versus this solid, this thing here is, and that's just not what we're talking about. Okay. Yeah. Yes.
But wouldn't some points such as z equals 0 and x be smaller than 3 and y be smaller than 2 be? I mean, wouldn't they make the equation true?
Say it one more time. I'm sorry.
If z is equals 0, x is less than 3 and y is less than 2, couldn't you hold true for this equation?
So
be part of it?
You're talking about a point like here?
Yeah.
A point like that? Yeah, so a point like that, z is 0, x and y are, I'm going to say, small, so let me just do it like this. Those are small,
Okay.
right? And 36 minus small is just not equal to 0. So this, very importantly, is not an inequality. This is an equation.
So the only points on that disk would be the ones that surround that circle.
Yeah. So this curve is literally part of the paraboloid, right? And that's the edge. That's the part of that's the edge of where we stop caring about the paraboloid, and all the stuff below there is what we don't care about. Is that cool?
Yeah, totally.
Okay. Yeah. Okay. So there's lots of potential points of confusion on that. Let me just say, be really, really careful about this. It makes a tremendous difference. And come talk to me after class if you're still maybe a little confused about, hey, wait a minute, why did we not include the gray on our surface? Okay. All right. So our surface, again, is like this. We're going to use surface independence. Surface independence means we look at the boundary. We just have to make sure that we preserve the boundary. Right? Surface independence means we get to pick any new surface that we want. Pick your favorite surface. Whatever you like. Any surface that has this same boundary. I have a personal favorite. There's many, many surfaces that have that as its boundary, right? There's something like that, I suppose, and I could imagine a glove, right, where this purple is that's the armhole, that's the hand hole where you put your hand in, right? Various different options. By far the easiest one to work with in most cases is going to be that flat surface. And if you have the ability, if your curve would permit a flat surface, having this curve as its boundary, take it. Right? It's bound to be the best choice. Okay. So the question that we were asked was to compute the flux through that surface. We're now invoking surface independence to say we're going to use that blue surface instead, making surface independence. And now I can pretty much throw away that green surface. Everybody good? Now, here's the little asterisk. You do have to be careful with orientations. Let's think through the orientations. Okay, so and I'm going to zoom so we can see this better. Yeah, that'll be good. So again, we have this surface like that, oriented, again, toward the z-axis that was given. And let's ask, what is the orientation that's induced on the boundary? And you got to remember, we have an arbitrary but standard convention on this, and you just got to follow the rule. You got to play the game every time. And the rule is right hand, thumb in the direction of the surface normal. Fingers of your right hand, see which way as they curl toward your palm, right? See how they define a swirl. And I'm going to say that the swirl on the surface will be kind of like that. Everybody see that? And now, what we're going to do is we're going to drag these swirls. I'm going to imagine taking these points, and I'm going to kind of drag down toward the edge and see how do these swirls, as I drag them down, how do they sideswipe up against that? Yes?
So if you point your thumb in this direction,
yep. So thumb sort of into the screen, if you will, right? Because it's into the screen, it's what you might call clockwise. As seen from where we're standing, it's going to look clockwise. All right, you see what I'm saying? Because this vector is going into the screen. Does that make sense?
Yeah.
Okay. The geometry is part of the challenge, right? It is what it is, right? So you just got to play this game. So inward swirls like so. And now let's just see what happens as I drag that. Let's see. Well, I'll tell you what I'm going to do. I'm literally going to drag it over here where it's a little bit easier to see. And how does that sideswipe up against the boundary? Well, it goes as I have it drawn there. It goes that way. How we doing? Everybody happy? Yep.
How do you know it's into the page?
Oh, because it said the statement of the question said oriented downward, right? And now so it says downward. So that means between these two different options, only one of these could in any reasonably sense be called downward, and that's this one. And then I just happened to notice that this one that is, I guess I could call downward, is also, I could think of that as being toward the z-axis. That's just the geometry of the circumstance. And it's going to be different for every surface. So please resist this temptation. There's students very often like to, okay, when I see a certain word, that means a certain thing. And, as some sort of an attempt to sort of bypass the geometry, and it doesn't work. You have to think it through every time. Okay, so we have our orientation, and with that done, now on our new surface, we get to ask sort of the analogous question. All right, well, what orientation on this surface? What orientation on that blue surface would give us the same orientation on the boundary? Because remember, that's the rule. The two surfaces have to have the same boundary, namely the same oriented boundary. So same orientation. Okay, let's play the game. Let's do it wrong first, just to see what wrong looks like. Suppose I said, "Hey, let's orient this S2. Let's orient that upward." Well, if we went upward and right hand and side swipes and all of that, we'd be going the wrong way. Does that make sense? Whereas, if we go up, wrong color. If we go downward, thumb down, side swipe, all that, and it goes correctly. Yeah.
Can you choose that in the opposite direction if you negate the integral and you get the opposite, or is that just
No, that works. I think there's a case to be. It's a little bit. See, the argument in favor of doing something like that, like if you're doing something with Green's theorem, then it really does make more sense because boundaries really only go the one way. Here, I don't need to introduce an orientation apology, right? Because I can just orient it correctly in the first place, and it's no harder to do it correctly than it is to do it incorrectly. Does that make sense? And so, I mean, it would get you the same answer. What that would do is it make your grader think, well, that was weird, And so, again, the goal is to make your grader, think that you're doing it the natural, the way that makes the most sense. Yeah. Yes.
So as soon as we're told that the parabola opens downwards, can we put our thumb in that direction and curl our fingers in the direction of the circulation, or do we still have to think about the inwards versus outwards?
The inward. Thinking of this vector as being inward was just kind of a different semantical take. Yeah, it doesn't make any difference. So if you think of this as being downward, the point is it's still the same vector, and you're still going to get the same swirls, and you're still going to get the same orientation. You do still have to think through, okay, what is that orientation? And then you do still have to think, well, on the new surface, what would induce the same orientation? All that's going to be the same. Yeah, yes.
So you talked about how since we know it's boundary independent, we can think of any surface that shares its boundary.
Yep.
What about the examples that you had shown all open upward, in the positive direction. If I just flip that across the XY plane, would it still work? Think of would that show the same? I guess would that show the same flux as the surface were negative of itself?
You mean sort of the reflection through?
Yeah.
Well, it'd be a different surface. You're saying you want to use that as the alternative?
It would be an inconvenient surface to work with. Okay,
Yeah.
So because like in
Yeah,
that
you could
case,
use
one
it.
direction is n.
Well, then you just got to play this game again.
Okay.
Yeah, and so I since there's nothing to be gained by such a choice, we can talk about it after class if you want, right? But yeah, I would call that sort of perfectly valid, but not particularly helpful. Yeah, totally. But yeah, you can totally do that. Yeah. Okay. Cool. All right, so we've got our new normal vector. Let's see. Let me get back to. Here we go. We were going to compute the green flux. That was the question. Surface independence tells us I can instead compute that blue flux. And all I did here is just separate the ds vector as in ds scalar. The reason for that is sometimes you get lucky with the geometry. I love this little normal vector here, this normal. I love those zeros. I love zeros, right? You probably like zeros as well. Zeros are awesome. They make stuff disappear. They make problems go away. So let's rewrite this in a way that allows us to see those beautiful zeros. And having done that, you can see that our vector field, our original vector field, nope. I'll use dark green. Okay. Our original vector field dot wrong color. Our normal this dot that is just minus xy. And so this integral simplifies really, really nicely. And in fact, this last integral that we're looking at here, and let's get rid of the mess. This last integral, 0 by symmetry. Now you'll notice I've left some details off there, right? I want you all to fill these details in. What's the plane by which you can argue that this integral is 0 by symmetry? Right? And to keep in mind, on an exam, such as we have coming up, you would have to indicate what the plane is through which you're making a symmetry argument. And there has to actually be a valid such symmetry argument as you claim. Right? So you do have to think through those details. You don't have to enumerate the details, but you do have to think it through, and you do have to be right. But anyway, make sure to fill in those blanks. How would you make a symmetry argument for this? And hint, there are two perfectly acceptable choices of plane that you can use. So think that through. Okay. All right, so let's just notice what a fabulously convenient solution this is. Now, we'll acknowledge that, we had to think through orientations and it had a geometric challenge, etc. But what else are you going to do in this situation? I could parameterize. That would work. But there's a lot of down that road. I mean, it's doable, but it's a lot of turn the crank. This is much better. Basically a snap. Right? Notice on the page here, the amount of algebra involved, practically nothing. Right? This is a great option. Okay, last thing on this one before we go on to the next thing, I want to show you another landmine. This is a real problem. This happens. I try to make a big deal out of things that happen a lot, and the bigger a deal I make, the less they happen. So, anyway, here we are. A lot of students will look at this, and they'll say, flux. Oh, my favorite theorem about flux is Gauss's divergence theorem. Gauss's divergence theorem, they think, says that a flux is a triple integral of divergence. And then they think, check it out, the divergence is 0. And that means that we're doing a triple integral of 0, and therefore 0. And some students will write this and proudly move on to the next page. And it is a catastrophe. Doesn't look like a catastrophe. This is an absolute faceplant catastrophe. The problem is huge. Oh my gosh! And y'all probably remember I made a big deal out of this at the time. Gauss's divergence theorem, right? The very first thing that the student is citing here. Gauss's divergence theorem only works if the surface is a boundary of a solid. This surface is not the boundary of a solid. Gauss's divergence theorem doesn't apply. And it's worse than that. It's not just that this integral isn't equal to this integral. It's that there is no triple integral. Remember, Gauss's divergence theorem says triple integral over the solid whose boundary is the surface. There is no solid whose boundary is this surface. Everybody see that? There is no such solid, therefore there is no triple integral. This is not this is not just an unrelated algebraic quantity. This is meaningless garbage. There is no triple integral at all. This is all nonsense. So be very, very careful about this. If you're going to invoke the divergence theorem, you've got to make sure that your surface is a boundary and this isn't. Everybody see the landmine? Make sure to double check that. Make sure to be 100% confident that you're actually talking about a boundary before you go around turning fluxes into triple integrals. Yeah.
So if it's not a closed shape, then you can't.
Correct. If it's not a closed surface, then you cannot directly apply the divergence theorem. Absolutely. Yeah. Now that was the perfect segue question. It's almost like I planted you to ask that question. There is a hack workaround. So the hack workaround, this is sometimes called surface closing. And it's kind of a tweak. It's technically a more powerful method than surface independence that we just used, but it's also more trouble to do. So anyway, let me just show you an example. It's best to just kind of dive right in. So here we have a new example question, and the question says we're looking at this surface right there. Again, not closed. Right? This surface is part of the sphere. This top face here is not part of the sphere. So this top space is not included. This is not part of our surface S. And it's through that surface S that we want to compute the flux of some vector field. Everybody see the question? Okay. So it's not a boundary. Well, dagnabbit. Well, how about this then? Let's just notice that if I were to say, hey, let's add in, now no fair, right? But let's add in that top face. Between the two of them, S in green and combined with D in blue, between the two of them, check it out, we actually do have a boundary, right? So all together between the two of them, we have a boundary, and specifically it's a boundary of this, what you've enclosed there, between the green and the blue. There is that solid region in there. So now we are interested in a boundary. Now, to be clear, S is still not a boundary, right? But at least there is a boundary on the page. Now I can at least entertain talking about the divergence theorem. And S is at least part of that conversation, right? So the hope is that if I apply the powerful theorem concerning this boundary, and if the thing that I'm actually interested in, the S flux, is at least part of that story, maybe I can solve for what I want. Everybody see the hope? Yeah.
Why is the normal vector up? Those spheres oriented down.
Yeah, that's right. Well, we always got to think, when you're thinking about boundaries, remember when you say boundary means oriented according to certain conventions. The convention when you're talking about the boundary of a solid is the normal is always away from the solid, right? So away from H is that way on the S region, and it's that way on the D region. Those are the outward, what you might call the outward normals. Is that cool? Yeah. Okay. All right. So now let's play it out and see how this goes. I am gonna. Whoops! Oh gosh. Let me clean up my picture here. The fluxes, follow this. S and D combined make the boundary, so the S flux and the D flux combined make the boundary flux. Just kind of rewriting that statement. This being a boundary, I can write down the divergence theorem. Now, to be clear, again, I cannot emphasize this enough. The boundary is not S, right? The flux through S is still not what the divergence theorem is addressing, but it's at least involved, and again, the hope is that I can solve for it. But this flux I can compute as this triple integral, like so. And so now, let's see, I can try to get this all on the screen. Looking at, oh come on, man. Looking at that equation, this is what I'm interested in. This is actually a straightforward computation. This top surface, super easy. That normal vector, 0, 0, 1. Gotta love it. Full of zeros. I love zeros. Makes this calculation really easy. F dot n simplifies. Just z. Z is a constant on that surface. This just falls apart into effortlessness. That's awesome. Right, so that blue calculation is easy. And then again, the triple integral on the solid, also easy because our divergence ends up being constant. Right? Our vector, by the way, I should come up here for a second. Our vector field was x, y, z. So the divergence is 3. That makes this calculation just a matter of looking at the geometry. And so I know the blue integral, I know the purple integral, and I can solve for the green by subtracting. Everybody see how that goes down? That's a slick move. I wish I thought of it. Somebody showed me this when I was about y'all's age. A very, very slick trick. And there are those circumstances where this is very, very valuable. Okay, now obviously if you're gonna be able to do this, you want to make sure that your top surface that you add in is not a nightmare, right? This is usually most convenient when the new surface, when the closing surface is simpler than your original surface. You also need the triple integral to be doable. So you want to make sure that divergence is, not something that would make your life harder. But when that happens, it works out great. Last comment on this is an exercise for y'all to think through, and I think this is a very healthy exercise. When divergence is equal to 0, if you execute this surface closing, in this case, when divergence is 0, you get exactly surface independence as a result. So it'd be a good one to think through. Take a few minutes to do that. Works out really nicely. Yeah.
For the example above, why are we now able to put like a lid on the surface, essentially like a discount top, and count it as part of this, like the whole?
Very importantly, we're not changing what S is, right? So S, throughout this whole discussion, S is never a closed surface. It's S combined with D. S plus D, between the two of them, is a boundary. I'm not saying that S includes D. I'm saying let's look at what you get when you combine S and D. Does that make sense? Yeah. It's a good question. Yeah.
So, I mean, like, it ended up being that boundary independence was good for the last question, but could we also use this method?
Yeah, that's right.
I guess a cap is like just a convenience, or it was an ellipse, but
yeah. So per this observation here, so when the divergence is 0, that's a special case. So let's see how to say this. Surface independence is this special case of surface closing. Yeah, absolutely. So you've already thought this through. Yeah, right. So good. Okay. All right. So this last thing here, you'll recognize these sort of the handwritten version of the diagram that I like to talk through. We've already done the talking through on this. The big thing to keep in mind is that this pattern holds wherever you put it on the diagram. Right? So here, or here in the two-dimensional case. Right? And that this is a very powerful, very convenient way to think of all these different ideas. And again, you don't have to memorize 3 times as many facts. You just remember one little pattern. And it applies just, wherever you might happen to need it. And while we're here, let me also remind you that all of our theorems, all of our big theorems, they all follow the same pattern themselves. So, for example, fundamental theorem of line integrals says if you take a gradient and then you look at the endpoints of a curve, this computation and that computation will give you the same answer. If you look at Stokes' curl theorem, that says if you take a curl and you look at the boundary curve of a surface, then this calculation and that calculation always give you the same answer. It's the exact same pattern. And likewise, if you take a divergence and if you look at a boundary surface of a solid, then that computation and that computation give you the same answer. So again, you can memorize these as 3 separate theorems, but if you think about everything in the context of this diagram, everything laid out just as it is, just as it sort of should be, it's really just one pattern. It's not 5 separate theorems. 3 here and 2 there. So really great way to think things through. Okay, let's see here. The last thing I'm going to do is talk about these examples. So by the way, we are kind of, in some formal official sense, done with Chapter 7. All the big ideas of Chapter 7 we're done. Right? So these next examples that I have here these are supplemental. These are, I like to do these when we have time. We seem to have about 3 minutes. I don't think we're going to get through 6 examples in 3 minutes, right? And I usually don't. It is what it is. The purpose of these examples is to just kind of remind you of all the different tricks and tools that we have, and specifically how you can use the diagram and how you can use these patterns that we've talked about to guide you through these computations, right? So see where you are on which diagram, do what the diagram says, and all of these examples, they kind of, this strategy of following the diagram will help you pretty much tell you how to solve any problem that you might encounter in this category of line integrals and surface integrals. So, since we aren't going to have time to go through them in class, what I'm going to do, and this tends to work out this way most of the time, in the COVID semesters, from home, I recorded detailed as I could be, everything I could possibly think of to say about all 6 of the examples on the next several pages. I made these recordings, gave them to my students at the time, and I'm going to just give you all those same recordings, right? So y'all can watch to your heart's content. These are, I think, really cool examples. They hit lots of the ideas that we've talked about through Chapter 6 and 7, mostly Chapter 7. But I hope you'll give them a look. I'm going to put those recordings on the YouTube channel probably this afternoon, the next hour or 2 probably. And feel free to, let me say it more strongly than that. I strongly encourage you to look at those to your satisfaction. I think it'll help you kind of bring everything together and see how we use this diagram, not just to marvel at the patterns, but how we use this for problem solving. How this will help guide you toward right answers. Y'all have a good rest of your afternoon. See you later. Yeah, give me a second to just turn this off.